Recording in progress.
Good morning, everybody. Hello. Welcome to our continued conversation about solubility equilibrium, where we are now going to frame what we understand about the solubility product and molar solubility of an ionic substance into what happens when we look at a precipitation reaction. So, in order to understand the relationship between solubility equilibrium and the process of precipitation, let's remind ourselves about what a precipitation reaction actually is. So, recall from Gen Chem 1, precipitation is a class of chemical reaction where ions undergo a double displacement and form a solid product as a result. So this is innately a reaction between two aqueous salt solutions that are then mixed. And as a result, new ion pairing or new ion association results in the formation of a new ionic compound. And this is insoluble. And thus we see a solid. So this is like the gist of precipitation. Mix two aqueous salt solutions, their ions undergo their little double displacement do-si-do, and as a result, we form some kind of insoluble solid. Now, in Chem 210, or Gen Chem 1, we used a list of solubility rules to predict the identity of our precipitate, which I'm going to abbreviate here as PPT. But now that we are in Chem 220, we understand that the reality of solubility is based on the ion dissociation equilibrium, which is something that is described via a KSP value, which relates, but is not the same as, to the molar solubility, S. So solubility, meaning the formation of like an insoluble product, has to be based on the ion dissociation equilibrium of that particular salt that potentially could be formed. So how do we then go from what we know in Chem 220 about like equilibrium being involved when we talk about a solution reaching its saturation point, and what's going on in our like kind of Chem 210 understanding of precipitation reactions in general? And the answer to that is we need to consider the total ion product, hereby labeled Q, at the point just before reaction to determine if a precipitate will form. And we do this by comparing our Q value to our KSP. So this is actually very similar, like this whole idea is the same idea as like Q and K in general equilibrium. So recall that Q, the reaction quotient, is product over reactants raised to their coefficients at some point that is not equilibrium. And K is the same, but it is at equilibrium. So we can make statements based on how Q relates to K numerically to say whether our reaction will shift or drive forward or shift or drive left in the reverse to reach equilibrium, right? So here, it's the same idea. We're going to be looking at Q and comparing that to K, and then determining if this means we have sufficient ions or not in solution to reach saturation. So this is called the total ion product because this is effectively the same as K. So it has the same form as KSP, but we are not at equilibrium, just like our reaction quotient. So for example, let's look at 3 different like reaction scenarios. So here's scenario 1. Here's scenario 2. And here's scenario 3. Okay, so scenario 1, let's call the beaker that I've drawn here on the left in each of these. Scenario 1, 2, and 3, where we're looking at Q, which makes the beaker on the right, where we're looking at where we've reached our saturation equilibrium. So Q and KSP, Q and KSP. So in scenario 1, let's consider a solution where at some point Q, we have that many ions in solution compared to when we are at saturation. This is where we see solid. And then we have our max number of ions possible that have been crammed into solution. So this is when we are at our saturation point. We are in that saturation dissociation equilibrium. So again, we can think about like K and Q, ion product, solubility product, as being like a placeholder that is like related to directly how many total ions we have in solution. It's not the same as that, but it's related to that. So here, Q, this ion product shows that I have fewer ions dissolved in solution than I would have were I to reach my solubility equilibrium, my dissociation equilibrium, or saturation. So in this case, we would say that Q is less than KSP, right? I could continue to add ions. So I can increase the number of ions, which means if I am going to, in my reaction where I'm looking at, again, just kind of a reminder to ourselves, we are looking at the point of solid. Where should I put this? Solid going to aqueous. This is what exists in equilibrium. Then it looks like I have the ability to put more ions into solution. So I can still add more solid. I could dissolve more solid because I have not yet reached saturation. So in this case, because Q is less than K, I am ion driven. So I would not expect to see a precipitate formed purely because I am still not at the point where I expect to see any kind of solid forming in my solution. I haven't crammed my solution with enough ions yet to reach this point of saturation. So that's scenario one. Let's look at scenario two. So scenario two is the inverse. So I've got Q that is going to be greater than K. So this is the point where I have so many ions in solution that I have indeed saturated things out. But compared to our total ion content in the left-hand beaker and the total ion content when we are at specifically saturation, you'll see that I have more ions forced into the aqueous phase than is technically what I could physically do based on the KSP and in turn the related solubility of that salt, meaning like I am over my saturation limit in terms of number of ions that could be found in the solution. So in order to reach equilibrium, I need to decrease my number of ions. And what happens when I decrease my number of ions? The only way I can like remove ions from my solution is if I precipitate those ions out into the solid phase. So I would expect to see a precipitate formed at these conditions where Q is greater than K. Too many ions then are allowed at saturation equilibrium. Okay, lastly, this leaves for us scenario 3. And this is going to be the scenario where Q and K are equal. So that's a little difficult to see. I'm going to do that in perhaps yellow. There we go. Q is equal to K. So let's see here. If I've got the same amount of ions in solution as I would expect to find represented in my saturated solution, then effectively I am already at equilibrium. So like, yes, I see a precipitation occur, but that's because I am like at saturation. So there is a precipitate, but that's because if Q is equal to K, I am at that saturation equilibrium point. So we are at saturation. And so we would begin to see the first traces of solid begin to form. So you can think about solution one, scenario one, as being undersaturated based on this Q. Solution two is being like supersaturated-ish. I mean, like we have a real definition for supersaturation. That's when we see these macrocrystalline structures form, but we've got too many ions compared to what is allowed based on the dissociation equilibrium of our salts. And then in three, we have just now the few first beginnings of a solid being formed, because this is just when we reach this point of equilibrium between solid and aqueous. So it is through these comparisons of Q and K that we can compare what's going on in our potential reaction or precipitation reaction by looking at the ion content before reaction has happened, but just after mixing, and then compare that to what we know about kind of the cap on our total solubility product as given to us by our KSP. So let's practice this. So will a precipitate form if 0.100 liters of a 1.00 times 10 to the negative 3 molar lead to nitrate solution is mixed with 0.400 liters of a sodium sulfate solution whose molarity is given there, 5.00 times 10 to the negative 4. The KSP of sodium nitrate and the KSP of lead 2 sulfate is 1.6 times 10 to the negative 8. All right. This is a lot of information. So since we are looking at a precipitation reaction, let's go ahead and identify our possible products that result from a double displacement. So I've got to look at my reactants. So I have lead 2 nitrate. This is PbNO3, and there are 2 of them coming together with sodium sulfate, that is Na2SO4. So polyatomic ions don't go away. And these are reacting to form some double displacement, which I always like to envision as like the cations are swapping anions, and make sure that you are charge balanced first. So make your compounds according to like proper charge ratios, and then worry about balancing with coefficients. So cation lead is going to be with the new anion sulfate. Lead has a +2 charge. Sulfate has a -2 charge. So this is one possible product. And again, we don't know if it's a precipitate or not. And then we also have sodium nitrate, which is a 1-to-1 compound. We don't know if this is the precipitate or not. And if we were to balance this reaction, we would have to double the amount of sodium nitrate made so that we are not breaking the law of conservation of matter. Okay. So these are my 2 possible products. The lead 2 sulfate and sodium nitrate. And you'll notice that I have given you in this problem the KSP of sodium nitrate. So I know what the KSP is of this product. That is 5.88. And then I also have the KSP of lead 2 sulfate, which is 1.6 times 10 to the negative 8. And it might be tempting for you to look at the value of K and say, oh yeah, we can totally immediately identify which thing is going to be insoluble versus not. Like we have a hunch that perhaps it's the lead 2 sulfate that might form a precipitate because its KSP, its solubility product, is much lower than the KSP of sodium nitrate. However, just looking at the KSPs is not enough. We need to actually consider the amount of ions that are present in this reaction mixture. So we need to look at Q, so we can determine in these reaction conditions if any of these KSPs are smaller or larger than the amount of ions that we could possibly have available to make each of these 2 precipitates. So let's look at our number of ions in solution that are like in the reaction mixture. So just after mixing, but before the reaction happens. So before any double displacement occurs, I've just now made this like new beaker full of ion soup, and I need to figure out if my relative ion concentrations are sufficient enough to drive my compounds, either lead 2 sulfate or sodium nitrate, toward their solubility point and thus form a precipitate. So let's start with the lead 2 ion, and then in turn the nitrate ion, because that's where the source of these ions is from lead 2 nitrate, excuse me. And then we also have the sodium ion and the nitrate ion. Okay, so real quick. There we go. So how do I figure out my lead ion concentration? I need to look at the compound that is the source of my lead ion. This is my lead 2 nitrate. I'm given a concentration and a volume, which means I can get moles. So let's do that. So I have 0.100 liters times 1.00 times 10 to the negative 3 moles per liter, and that's of the lead 2 nitrate. And I also know that for every 1 mole of lead 2 nitrate dissolved, 1 mole of lead 2 ion is put into solution. That is from looking at my 1:1 ratio, aka my subscripts in the lead 2 nitrate formula. So this gives me 1.00 times 10 to the negative 4 moles of lead 2 ion. And I need the concentration just after mixing. So I cannot use this same volume. I need to consider the volume after mixing. So this is going to be equal to my 0.1 liters plus my 0.4 liters. So this is over 0.5 liters. So I'm dividing by 1/2, which is the same thing as doubling. This becomes 2.00 times 10 to the negative 4 moles of lead 2 plus. And then I can do something very similar for the nitrate. So this is 0.100 liters times 1.00 times 10 to the negative 3 molar. Except now, looking at the ratio of my salt to its ions for every 1 mole of this lead 2 nitrate dissolved, that generates 2 nitrate ions. So this is going to become 2.00 times 10 to the negative 4 moles of nitrate over our total mixture volume, 0.500 liters. So 2 divided by 1/2 is 2 times 2, which is 4.00 times 10 to the negative 4 moles of nitrate. Hold on, I put nitrate twice. I want sulfate here. Okay, let's move on to sodium sulfate. So we're just doing some more like Gen Chem 1 style mole calculations. So Na plus, so we're looking at the sodium sulfate now. This has a different molarity and a different volume. So we had 0.400 liters times 5.00 times 10 to the negative 4. And then let's look at the mole ratio in sodium sulfate to sodium. So for every 1 mole of Na2SO4 dissolved, that puts 2 moles of Na plus ion in solution. So let's do this real quick. 0.4 times 5 times 10 to the negative 4. And then times 2. That's 4 times 10 to the negative 4 moles of sodium ion over our total new volume just after mixing. Because again, we are thinking about like the amount of ions available in this reaction mixture that we're going to have to compare to the amount of ions that could possibly be present if one or more of these substances reaches its solubility, its saturation point. So we're doing 4 divided by 0.5. This becomes 8.00 times 10 to the negative 4. And excuse me, I've been labeling these all as moles. These are molarity. Molar Na plus, and then we can do the same thing, knowing that our sodium sulfate has a 1-to-1 between the salt and the sulfate. So that's going to be 2.00 times 10 to the negative 4 moles of sulfate over our total volume. Okay, this is going to be half as much. And now we need to take all of these molarities, specifically for like the lead and for the sulfate, and then respectively the sodium and the nitrate, and figure out what our Q is for each of these. And only through comparing our Q to K can we determine if one or more of these things will form a precipitate. Nope. So let's go ahead and double this slide just so we have some room to finish our thoughts. Okay. I'll do a bunch of erasing. I know this must be very fun to watch. Okay. So again, in looking at our KSPs, we have a hunch that it might be the lead 2 sulfate. That is going to be the one that reaches its saturation point, aka it precipitates out first, it becomes a solid. But we only know that if we were to look at Q. So let's look at Q. For the potential formation of lead 2 sulfate. So let's write out that saturation equilibrium. This becomes lead 2 plus and SO4 2 minus. And so my Q is going to be concentration lead 2 plus times concentration SO4 2 minus. So this is going to be our 2.00 times 10 to the negative 4 molar times our 4.00 times 10 to the negative 4 molar. This gives us 8.00 times 10 to the negative 4 molar squared. And KSP was 1.6 times 10 to the negative 8. So in this circumstance, do we make a precipitate? We have Q that is way greater than K. So we would expect to see a precipitate formed here, right? Q has a huge amount of ions compared to what's allowed at saturation. So we are going to then convert some of these ions into solid, moving this way, in order to achieve equilibrium at our saturation point. So we do expect to see lead 2 sulfate form a precipitate under these reaction conditions. But now let's also just kind of sanity check that we would not see any solid sodium nitrate. So let's look at what would happen if we were to reach the saturation point of sodium nitrate. So Q for this is concentration sodium times concentration nitrate. So that's going to be equal to our 4.00 times 10 to the negative 4 molar times our 8.00 times 10 to the negative 4 molar. All right, let's just real quick do what that is. 4 times 10 to the negative, oh goodness, okay. 4 times 10 to the negative 4 times 8 times 10 to the negative 4. That gives me 3.2 times 10 to the negative 7. That's what Q is. And notice KSP is like over 5. So since this Q is significantly less than K, we have way fewer ions than are allowed at our point of saturation. So we, at these reaction conditions, do not have the capacity to make a precipitate out of sodium nitrate because we do not have a sufficient amount of ions to hit saturation, right? We can still cram more ions into solution. So this is how we predict whether or not we expect to see a precipitate in a precipitation reaction. We utilize a comparison between the KSP and our reaction conditions at some point Q, the ion product. In our next slide, we are going to talk about the idea of selective precipitation and how we can take advantage of the fact that different KSPs and thus different solubilities of different salts are going to allow us to separate certain ions out of solution without affecting others. So coming up next is selective precipitation. I'll see you very soon.